In this video, we're going to go over why we need a list and the basic operations on lists. All right, so here is our average toPrice function. It takes in two items. Those are the prices of those items. All we do is that we sum them all up and then divide by the amount there are to get the average of the price of the two given items. So that's all well and good, but what happens if we want to upgrade this function to handle three things? So we run this code, immediately we're hit with a problem, and that is that we can't have two functions with the same name in the same scope. So immediately this has to be average 3 price. What else would need to change? Well, the signature would need to change, like so. Item 3 now, right? The purpose statement is also out of date. Produce the average price of two given items. Well, we had to upgrade you to 3 now. And the code of the function body needs to change like so. All right, so let's just recap what we needed to change to upgrade average 2 price to average 3 price. All right, in total, roughly 4 things. We needed to write a new function name, write average n price, where this n is at 3, to upgrade this to this. We needed to change the purpose to handle 3 items instead of 2. We needed to change the number of parameters the function takes, like so, right? And then change the code of the function itself. Divide by 3, divide by 2, sum 3 items, instead of sum 2 items. All right, so this gets worse and worse as we had to create a new function to handle more data, right? Imagine an average 4 price. We had to do these 4 things again. I'm not going to do it, but just imagine that as we handle more data, we had to write more functions. And it gets worse as the number increases, right? So a 10 argument function, 20 argument function, 50 argument function, it gets worse and it's just not sustainable. All right. So I just wish there was a data type that can store multiple values, right? Sort of in one type. And there is. Structures can hold multiple values in one type. So let's try that. So here's the same problem, but we're going to use structures because structures, right? If you remember, can hold things inside it, right? It can hold multiple things inside of one type, one sort of variable, if you may. Okay. So we have defined struct cart, and cart is going to hold all the items. All right. Cart is make cart number. So these are numbers and those, each item n. So item n is its price, right, of that item. All right. So let's look at the function. It's the same as our average 2, right? But it takes the cart this time rather than the items individually. All right. All right. So it produces the average price of all the given items in the cart. All it does is it takes the items, item 1 and item 2 of that cart out. It sums them up together and divides by the amount there are, of course, to produce the average price of all the item the cart holds. All right. So we run this code. It's all well and good. Let's do the same exercise as we upgrade this to handle 3 things. Let's see what needs to change, right? Well, the data definition would need to change because you would have to be able to hold 3 things now, right? Like so. Number. All right, what else we need to change? The interpretation is fine, right? It's still relevant. Each item n is its price. All right, what about the function itself, right? In the process of upgrading this to handle 3 things, what needs to change? Well, the signature really doesn't need to change. We don't have to do average 3 cart, right? Because the name is still pretty descriptive of what it does when it averages 3 things this time. And it still takes in a cart. We don't have to add an extra argument or anything. It's all well and good. What about the purpose statement, right? Produces the average price of all the items the cart holds. That's still pretty relevant to the problem description as we upgrade this to handle 3 things, right? Let's see what else needs to change. Let's see. We have to, we have to take the 3rd item out of the cart, item 3, and put it so that we can sum it all up, all right? And then we also have to divide by 3. All right. And then we run this code. The constructor also breaks. All right. Okay. So contrast this to when we were doing the arguments individually, right? A lot of things needed to change. 4 things needed to change, right? In our case, really only 2 things needed to change. The data definition itself and the code, right? These are still relevant, all right? So it's all well and good, but we're still not there yet, right? Even though structures can hold multiple pieces of data, we still run into the same problem, and that is our cart right over here. It's fixed size, right? It must only hold the amount of data, only the amount of items we tell it to ahead of time as specified by these fields right here, right? This is not realistic. In the real world, when you go shopping, you kind of don't know the amount of items you want to buy. You kind of grab things along the way. Maybe you change your mind and you put something back, right? And really you figure it out along the way. In other words, it can be arbitrarily long, right? The amount of items in a shopping cart can fluctuate between 5 to 20, again, because you put things in and out of your cart all the time. So if only there was a data type that was more flexible, that can grow and shrink on demand. And that is what lists are for, all right? It's going to make it so that we don't have to change the data definition or the function definition, just the data itself, all right? So we're going to be able to do something like this, where we can just do something like, hey, I want to buy all these things and here's all the prices of them. Oh, wait, never mind. I changed my mind. I want to buy 2 things now. No, I want to buy 3 things now. Like so. We would only need to change the line of the data itself. All right. So a list. What is a list? Well, a list is a compound data type, right? Similar to structures. Structures are a compound data type, right? But the big difference is that it can grow and shrink on demand. So BSL will treat a list as a single value, right? That could contain other values inside itself. Again, very similar to structures. The main difference is it can grow and shrink on demand. So you can imagine a shopping list, right? You write down milk, eggs, cheese, etc. on a piece of paper, then fold up the paper and put it in your pocket. While it's folded up, you can think of the list as a single entity. Right? It's only later at the store when you need to go into the list and retrieve the individual pieces of information out of it. So let's go over the basic syntax for lists. Okay, so there's the empty list, right? If we run this code, it should print like this, right? It sometimes prints like this, quote, parentheses, parentheses, all right? I'm gonna copy this here and run it off to the side. It's still valid code, all right? So this is important, and it's that these two are the exact same thing. In fact, you can imagine someone did this, define empty to be bound to this empty list. BSL does this and provides us with the variable empty for our convenience. All right, so these two are exactly the same. I'm going to use the first version probably most often. You might see me use the second version as well. Don't be confused. They're the same thing. I'm going to use the first version more because we can deal with less parentheses. All right. So an empty list, you can imagine it being sort of like an empty piece of paper, right? A list has to exist on something. So that is the empty list. All right. So how do you put things in a list, right? And that's what we use cons for. So cons is struct for construct, right? So it takes in as its first argument anything. The second argument is a list, and it produces a list, all right? So short for construct, cons produces a list, all right? So let's do some lists right here. Define stuff. It's gonna be cons false onto empty, all right? And how do you read this? Well, you read it as put false in front of the empty list, right? It's kind of weird, all right? And this is a 1-element list. There's only one item in here, and that is false. Let's do some more lists, right? Define groceries, cons eggs on a cons chips of empty, all right? There we go. So let's read this the same way we read stuff, right? So put chips in front of the empty list, right? That's what cons is for. And then for this other cons over here, put eggs in front of that. All right. So it's all good. Let's do another list. This time let's make it numbers. So numbers ls. We can do cons 4 on a cons 3 on the cons 6 empty. All right. So likewise, this is a 3-element list. There are 3 items in this list, 1, 2, and 3. Likewise, the list we created earlier is a 2-element list. There are 2 things in this list, and those are just eggs and chips. I'm gonna use some chips right now. All right. So we can also mix types in here, right? So let me do something like whatever ls. Let's say cons 9 on a cons true on the cons ASDF and then empty. All right, like so. So this was a list with all strings. This is a list with all numbers. And I just wanted to show that we can put anything in the elements of these lists, right? There's a number here, a boolean here, and a string here, like so. All right, so I'm gonna copy some code here I have here off to the side. Let's run this, all right? So this is just some silly code. I want to show that, well, the evaluation rules stay the same, right? In order for cons to do its job, right, all of its arguments has to be values, right? And really remind yourself that cons takes as its first argument anything. So we see here that that anything is a boolean, right? That any is a string in this case, and it's a number in this case. All right. So evaluating this, right, we get cons ASDQ. This is going to be a one string at the end of the day, and this is going to be 8. So try to guess how many elements, right? How many items are in this list? Spoilers in 3, 2, 1. It's 3 things, right? This is the first thing. This is the second thing. And this is the third thing, right? The third element in this list. We just run this code and we'll type OP, and we should see it fully evaluated, right? This is that 8, and this is that string. And there are 3 elements in this list. Let's keep going. So there is the first function, and this takes as its first argument list of anything and produces the first element of the list, right? So it produces the first value of the given list, assuming a non-empty list. All right, so what's first of stuff, right? Stuff over here, right? This is going to grab the first thing in that list, and that is going to be false. So we just see false over here off to the side, and so we do. What about first of groceries, right? Try to guess what that is, right? The first of this list. And it is, drum roll, eggs. All right. So we just see eggs. We run this code off here to the side. So we do. What about first of numbers ls? You can guess what that is, right? The first of this is going to be that 4. All right. If I spelled numbers ls right. Whoops. All right. Likewise, all right, the purpose statement produced the first value of the given list, assuming a non-empty list. This is important because what would happen if we gave it an empty list, right? So first of empty, right? Guess what it does? It's going to crash the entire program because it says, hey, I'm assuming that you gave me a non-empty list. You gave me an empty list. What are you doing? Read yourself, right? So likewise, these two are the exact same. This one looks kind of more like an empty list, right? It looks like there's nothing in here. I'm trying to get the first thing in here, and there's nothing in here, like so. So I produce a crash. All right, let's go over the next function, rest, right? So rest takes as its first argument list of any, and it produces a list of any. All right, so it produces a list with the first element excluded, assuming a non-empty list, like so. So what's the rest of stuff? Right, what's the rest of this list? Well, it's going to get the rest of this list, which is going to be empty. I'm going to run this code, and we should see the empty list. All right, what about the rest of groceries? Right, this list right here. All right, try to guess what that'll be. Spoilers in 3, 2, and 1. Well, this is the first of the list, right? And this is the rest of the list. So it's going to be cons, chips of empty. All right. And likewise, you can guess what the rest of numbers ls is going to be, right? This is the first of numbers ls, which is that 4. And then this whole thing, right? This entire whole chunk is going to be the rest of the list. So we'll run this and we should see cons 3 and 6, like so. All right, so it gets us the rest of the entire list. All right. Also, it's the same as first, and then it assumes we're giving it a non-empty list. So if we give rest an empty list, it's going to say, hey, you got to give me something that has something in it, like so. So it's going to crash. Okay. So here's a quick brain teaser for you. All right. So how do you get the second element of the list, right? Right. Get me chips from groceries, right? Get me the value, the string chips from this entire list using a combination of first and rest. All right. That's how you're going to have to do it. All right. Just a reminder that rest doesn't give us the second element of a list, right? It gives us the rest of the entire list. We want the second element of the list, which is string, not the whole thing that comes with it, like so, right? All right. Like similar to this numbers ls here, right? Rest would give us this entire list. Cons 3 of 6 onto empty, right? We just want the 3. We don't want the whole thing that also comes with a 6 and stuff. So, spoilers in 3, 2, and 1. Combination of first and rest. All right. So here's how we're going to do it. The trick is that if we call rest of groceries, right, to get the eggs out, we're going to be left with this, cons chips of empty. So let's just run this, right? So we take the rest of groceries, and then we're going to take the first of that, which will get us chips, right? So the rest of groceries, right? Rest of groceries will get us here, and then we're going to take the first of this to get chips out. So I'm going to wrap this like so. And that is how you get the second element of a list out. So here's our string chips, not with everything else attached, right? The empty list attached with it. Likewise, we can do the same with the numbers. So rest of numbers ls, right? So rest of numbers ls will get us the rest of this list, right? Which will get us here, but it doesn't get us the second element and gave us this whole chunk out, right? So we should see cons 36. And if we take the first of that, right? First of this rest, then we should get the 3 out, like so. All right, I'll run this code, and we should see the 3 right there. So what do you think would happen if we tried to get the second element of a 1 element long list? All right, I'm going to run this off to the side here. This list is 1 element long. What happens if we try to get the second element out? Well, there is no second element, right? There's only one element. There's only one thing in here. So we're going to do rest of stuff, which will give us this empty list, right? And if we call first on the empty list, right, then that's going to crash and say first, hey, you got to give me something that is not an empty list. All right. So let's do one more. All right. So how would you get the third element of your list out, right? The third element of list out. So there's only a few lists here that has 3 elements, right? This one has 2 elements. This one has 3 elements. And this one has 3 elements. So try to get me this number 6 out, right? With a combination of first and rest, right? You're going to have to use the 2. So get me the number 6 out of the numbers ls. Try to think in your head how you would type this out. Spoilers in 3, 2, and 1. So it's going to be rest of numbers ls. All right. So that'll get us here, right? But we're still left with this list. So we have to call rest again on this list to get us here, and then first to get us the 6. All right. So again, rest of ls, the rest of numbers ls will get us here, right? So we should see cons 3 on the cons 6 empty. If I type numbers ls right, like so. All right. So that rest got us here. That's why we see this here. And then we have to take the rest again of that. Rest again. To get us here to cons 6 empty, right? And then we have to take the first of that to get us that 6, right? Like so. First. And we should get the number 6, right? Likewise, if you give it a 2 element list, when we're trying to get the third element list, right? A list that is only too long, there is no third thing, there's only 2 things in this list, and it's going to crash, right? So these 2 operations are very common to do in Racket, and they provide us with a function called second that does exactly just this, combination of first and rest, right? So give me the second item of groceries. So the name is second, groceries, and we get chips, second of number ls. This is the number is ls. This is the second element. We should see that 3. If I keep spelling number is wrong, like so, all right? So I don't want you to use second. There's also third to get the third element of list. Try to avoid using that because you guys should get used to using a combination of rest and first, all right? In a couple, videos, maybe like after 5-10 practice problems or so, then you can use second and third. But for now, just try to avoid them. You have to get used to, seeing this rest and first combination. So let's keep going, all right? There's empty right? Empty question mark, all right? And this function takes anything as its first argument and produces a Boolean, like so. So it produces true if given an empty list, false otherwise, all right? So empty right? Empty question mark. It's one letter off from empty, all right? So just be careful of that. All right, it takes in anything, so we can give it anything we want. We can give it a Boolean. I'm going to run this code, and we should see false. I'm going to type it here instead. We can give it, a number, like that. It's going to reduce false. It's not going to crash, right? It's all good. We can give it a string. It's not going to crash. It's going to say, hey, what you gave me is not empty, right? The only case it's going to produce true is if we give it an empty list. So empty, empty, and in case you didn't believe me that these are the same, right? The typed out empty and this quote parentheses, let me see, empty parentheses question mark. Whoop, my bad. Like so, it's true. Okay, and likewise, if we gave it like a list with one element long, like stuff, right? It's not empty. It's not an empty list, right? There are things in this list. So I'm gonna do it down here. So empty of stuff produces false. I'm going to run this off to the side like so. All right. So there's also cons all right. And it takes in anything and produces a Boolean. And it determines whether some value is a cons list. All right. So if we do cons again, it takes in as its argument, first argument, anything. So we can give it a number. It's going to produce false. It's fine. It's not going to crash. Cons right, is the thing you're giving me a constructed list. So we're giving it a string this time. We should also see a fourth false right here. So here's our fourth false. So we can give it anything we want, numbers, strings, booleans, etc. All right. What happens if we give it the empty list, right? Is cons of empty, right? Is this a cons list? Is empty a cons list? Well, it's not a cons list. So we should see our fifth false right here. All right. The only time it's going to produce true is if we give it a cons list. So cons, let's say moo onto empty, right? That should produce true. So like so. And if we give it any of our other lists right here, right? Like cons stuff, cons of stuff, I mean, it should produce true, right? Because these are all cons lists, like so. All right. And finally, let's go over the last function that we might see. So it's going to be list right? List question mark. It takes this as its first argument, anything, and produces a Boolean. All right. So its purpose is that it produces true if given any kind of list, empty or cons. All right. False otherwise. So this predicate is the same as pretty similar to these, right? We can give it anything we want. I'm going to do it here, right? So list list question mark. I pronounce the question mark here as right? List of, let's say, is this an empty list or a list? No, it's not. It's not an empty list or a cons list. So we could give it strings. We can give it numbers. That's fine. It's not going to crash. It's going to say, hey, what you're giving me is not a list. We're just going to produce false. It will produce true, again, if we give it a cons list. So cons, let's say ASDF, and then onto empty, right? That's a cons list. Produce true. And also the empty list itself, right? List of the empty list will also produce true, like so, right? It's an empty list, but it's still a list nonetheless, right? It's going to produce true if we give it any kind of list. So let's review the data definition for a list because it's a bit weird, all right? A list is one of either the empty list, so here is all our empties, or a cons, right? A cons structure where the first argument is anything. So this any is true, it's a Boolean, right? Any means any type, so then in this case it's a Boolean, in this case it's a string, and in this case it's a number. But its second argument, second position, has to be a list itself. So there's a self-reference going on here, right? And because there's a self-reference, we see this sort of nested construction, right? So this cons is nested inside this outer cons, all right? Likewise with here, this cons is nested outside this one, and this one is nested inside this one, all right? And that's why we see this sort of weird construction, all right? So the number one mistake students make is that they don't trace the data definitions, all right? So is empty a list? Well, what is a list? We need to go look up the data definition. Is empty one of these, right? Yes, it is. So there we go. What about this one, right? Is this a list? Does it fulfill the contract of cons right here? Well, this, if we will go look up what a list is, we're going to find that it doesn't match this empty, right? But it does match this cons of any list. All right. So it's very important to make sure your signatures match the data definitions like so. So I have an example down here. Let's do a quick exercise. All right. So this is an invalid construction of a list. And I want you to pause the video and look at the data definition and this signature right here and explain why these two are an invalid construction of a list, all right? Spoilers in 3, 2, and 1. All right, so cons, this type does match this any right here. This second argument, though, it's a bit problematic, right? For this cons list, right? This is a list because cons takes as its second argument, right? This is the first argument. This is the second argument, right? A list. Is this a list? Well, we gotta go explore and check it out. So list is one of empty, so it's not that. But is it cons, any, and then a list, right? There's nothing here for this empty. There should be an empty here, right? And that's not the case. The problem with this is really that this cons, outer cons, has 3 arguments. This is the first argument, this is the second argument, and then this is the third argument. So someone, put this empty where it's in this outer cons when it should be in this inner cons right there, right? And for this second case, right, define nums on the cons 3, define nums as cons 3, 2, right? Cons takes as its second argument, right, a list. This 2 is not a list, right, because it doesn't match empty and it doesn't match another cons list, right? And if we have this in racket, it'll give us an error actually. So I'm going to comment one of them out. All right. And it's going to complain that, hey, you gave us 3 arguments. This is the first argument, this is the second one, and this is the third one. All right. And then this bottom one, like so, it's going to say, hey, this second argument is not a list. So a good visual analogy are Russian dolls, and the Russian dolls hold smaller ones, which in turn hold smaller ones, which in turn hold smaller ones, like so, all right? That's how we're nesting sort of structures to represent a sequence of data, which is represented by the idea of a list. All right, so we're not always going to be writing lists like this, right? In this cons, true on a cons Venus, and like in this long nested sort of chain-like way. But we want you to continue writing it like this until we upgrade the language level where there's going to be a much easier way that we can write lists, right? But for now, we need you to continue writing lists in this sort of cons list style way so that you guys can get really familiar with the inner structure of a list.